Alright, this video is on empirical formulas. Mainly what an empirical formula is a formula representing the smallest ratio of the different atoms within a compound. So for example, if I had, I don't know, C6H12O6, this would not be considered an empirical formula because I can reduce the subscripts. So if I was to divide each one of these subscripts by 6, I would get H2O. And that would be the empirical formula versus this being the molecular. This would be the empirical. No P. Empirical formula. Now, the steps to calculate empirical formula are written on page 201. They're in a table, okay, but they're also in section 6.3b. But what I'm going to do on this video is show you some examples of how to calculate empirical formula. So let's go ahead and take a look at the first one. Okay, so we have two masses right here. We have 4.151 grams of aluminum and 3.692 grams of oxygen. In order to calculate the empirical formula, we need to convert both of these into moles. And this makes sense considering that an empirical formula is showing the lowest ratio of different elements within a compound. But what you're really showing there is within that compound, what's the molar ratio within the compound. So for example, if I was looking at H2O, okay, I'd have 2 moles of H for every 1 mole of O. So now what we do is by converting the grams of aluminum into moles and the grams of oxygen into moles, we can get a molar ratio from one element to another. Okay, so let's go ahead and knock this out. We have first 4.151 grams of aluminum. Put that over 1. I want to get to moles. So I would use molar mass. Molar mass of aluminum is 26.98 grams of aluminum for every 1 mole of aluminum. Okay, and that answer is 0.1539 moles of aluminum. Go ahead and take a look at the oxygen, 3.692 grams of oxygen. I also want to get this one to moles, 16.00 grams of oxygen for every mole of oxygen. That answer is 0.2308 moles of oxygen. Now, once I have these to moles, what I want to do is I want to look at which of these numbers of moles is the least. So in this case, aluminum has the lower number of moles for these two particular masses. So what I'm going to do, okay, I'm going to hold on to those measurements right there, okay, and I'm going to divide each of these moles, okay, moles of aluminum and moles of oxygen, by the lower number. So I have 0.1539 moles of aluminum. Okay, I'm going to divide that by 0.1539, and obviously I would end up with 1.000 moles of aluminum. I'll do the same thing down here for the oxygen, 0.2308 moles of oxygen, and I divide by 0.1539 equals 1.508 moles of oxygen. So now what this is telling me is that the molar ratio between aluminum and oxygen is 1 to 1.5. Now obviously this decimal right here can't stay there because we cannot have a subscript with a decimal point. But one way we can get rid of this, of course, is to double it. So the same thing as saying that it's a 1 to 1.5, I can also say it's 2 to 3 ratio. Okay? And of course, I have a 2 aluminum to 3 oxygen ratio, I would write that like this. Aluminum 2O3. This would be the empirical formula for a sample that has 3.692 grams of oxygen and 4.151 grams of aluminum. Okay, this is what you'll be finding right there. Okay. Now I know this is the empirical formula because I cannot break these numbers down to any whole numbers that are smaller. All right, so let's take a look at another example. Okay, so we have 0.5346 grams of vanadium, and we have 0.6330 grams of oxygen. Calculate the empirical formula. So like I said, first thing we're going to do is convert both of these values into moles. So I'm going to go 0.5346 grams of vanadium over 1. Okay, the molar mass of vanadium, which is number 23, is 50.94. For every 1 mole of vanadium. Okay, and I'll end up with 0.006961 moles of vanadium. Okay, then oxygen, 0.6330 grams of oxygen over 1. For every 1 mole of oxygen, I have 16.00 grams of oxygen. And I'll end up with 0.01740 moles of oxygen. Of course, this number is smaller than the moles of oxygen. So what we'll do is we then divide the moles by the moles of each element by the lowest number of moles, or lower number of moles, in this case the vanadium. So I would go 0.006961 moles vanadium over 0.006961, and of course I get 1.000 moles vanadium, 0.01740 moles of oxygen divided by 0.006961. My answer ends up to be 2.500 moles of oxygen. Okay. So of course what this means is there is 1 vanadium for every 2.5 oxygen, which we wouldn't write with a decimal. So we'll go 2 vanadiums to every 5 oxygens. And of course that translates into V2O5. And that's our empirical formula. Okay, another way you'll see problems like, or different types of problems, but you're going to solve for empirical formula, is if you have percentages of each element. So if you have the percent composition of each element within a compound, we can still determine the empirical formula. For example, I have 50.8% cobalt, and I have 49.2% fluorine. Okay, so the easiest way to go about this is just change them into masses, because the amount of cobalt and the amount of fluorine in this compound isn't going to change. It doesn't matter if I have 1 gram of it, or I have 100 grams of it, or I have 1,000,000 grams of it. It's not going to matter. It's going to be 50.8% cobalt and 49.2% fluorine. So why not make it easy on yourself and just change this to 50.8 grams and this to 49.2 grams, assuming that you had 100 grams of that substance. Okay, so from there, we'll do what we were doing in the last one, which is getting the number of moles. Grams of cobalt over 1, mass of cobalt, 58.93 grams of cobalt over 1 mole of cobalt, Okay. This equals 0.3 sig figs, 862 moles of cobalt. All right. Take a look over here with oxygen, 49.2 grams of fluorine, or sorry, not fluorine, oxygen fluorine, over every 1 mole of fluorine, we have 19.00 grams of fluorine. So the number of moles is 2.59 moles of fluorine. So of course, that one's lower. So we will divide both of those number of moles by the lowest number, which would be the moles of cobalt. So 0.862 moles of cobalt divided by 0.862 equals 1.00 moles of cobalt. Do the same thing. 2.59 moles of fluorine divided by 0.862, and I'm going to end up with 3.00 moles of fluorine, which means there's 1 cobalt for every 3 fluorines. So I would write that like this, COF3. And there is your empirical formula. That would be cobalt-3 fluoride. Because cobalt is a transition metal, it could have multiple charges. In this case, because fluorine has a -1 charge and there's 3 of them, it must be cobalt-3 fluoride. All right? So, this is mainly how you calculate your empirical formulas. Okay? If you want to do some extra credit, you can refer to section 6.3c, and that will tell you how to get the molecular formula, which is not the same as empirical formula. Okay? Because just because this right here is the whole number ratio does not mean that it's the actual ratio of the molecule, or in this case, the formula unit. But if you look at 6.3c, and there are some practice problems that you can do out of the textbook. Just look at the table of contents, and you'll be good to go. This extra credit, or problems from this extra credit assignment, will be on the test, so it can actually translate to having extra credit on the test.